Hi, welcome to this presentation. The title of the presentation is EEG-based emotion recognition using variational mode decomposition and convolutional neural networks for effective computing interfaces. I am Tachin and my co-author Professor Sabramalai Manikandan. We are from the Department of Electrical Engineering, IIT Palakkad, and this work was supported by Professor Linga Reddy. He's from the Department of Information and Communication Technology from the University of Agder, Grimstad, Norway. We'll start our presentation with the outline. So we'll have a quick introduction on the title and the literature review that we have done, and then the proposed method and the results that we have got, and then we'll go to the conclusions and subsequently to acknowledgement and references. So coming on to the introduction, now human emotion recognition is basically identifying emotions based on some physiological signals such as EEG or heart rate, ECG. It could be used in assessing mental stress or predicting emotional wellness of an individual under stress, and it even has applications in affective computing, which could be facilitated using faces, human computer interactions, and it has applications in brain to brain communication. Human emotion recognition can be done using many signals such as EEG or skin responses or electrocardiograms or PPGs, speech signals, and even facial image signals. EEG signal is extensively used in human emotion classification prediction problems because EEG signals have highly relevant emotional information as they are recorded by placing the electrodes on the skull, and the 5 brain waves that we are extracting from the EEG are associated with the functional tasks such as anxiety, concentration, awareness, alertness, and sleep, and they also result in higher accuracy as compared to other emotion related signals. Coming on to the literature review, in the past studies, EEG-based emotion recognition methods were presented by extracting one or more features in time domain, frequency domain, or time frequency domain, such as in short-time Fourier transform or wavelet transformations. And learning classifications that has been used in previous research works include KNN or artificial neural networks. And we've also seen that differential entropy has outperformed other features, and it was shown in 2013. And it was also shown that the gamma brainwaves are highly associated with emotional state than any other brainwave. Coming on to the other literature work, we can see that there's a work that proposes a cross-subject emotion recognition method based on flexible analytic wavelet transformation, which uses a channelwise SVM and RF classifier, and an average classification accuracy of 83.33 was achieved. And we've also seen research works done using DNN and automatic channel selection based methods, and they have got an accuracy of 86.65. So we have inferred from the previous research work that we need to develop emotional recognition models robust to noises and artifacts using deep learning networks. Now, the existing challenges in there are selection of optical hyperparameters or selection of the activation functions, increased computational load, presence of noise and artifact. Now, coming on to the major contributions of this paper, we have proposed a 2-stage VMD-based noise suppression and brain wave extraction for low-frequency artifacts and brain waves, such as delta, theta, alpha, beta, and gamma. And the optimal parameters of VMD are presented. We have also investigated the robustness of DE features extracted from brain waves that we have listed above, and we have also identified optimal CNN architecture by exploring best hyperparameters and achieving the highest accuracy with reduced computational time and model size for 3 number of layers, 2, 5, 7, and each with 4 activation functions to find the best activation functions. Now coming on to the proposed CNN-based emotion classification. So the proposed method is that we do a VMD-based LF artifact removal, which is a low-frequency artifact removal. Once we have the clean signal, brainwave construction and a high-frequency noise suppression is done using VMD, and then features are extracted. Once the feature are extracted, these features are fed into a CNN-based emotion classification model. Now, coming on to the variational mode decomposition, which we have used in order to reduce the low-frequency artifacts and to decompose our EEG signal into brainwaves, or the construction of the brainwaves. Now, VMD is an adaptive quasi-orthogonal signal decomposition technique that can non-recursively decompose a multi-component signal into a finite number of band-limited intrinsic mode functions. So VMD is actually a constrained optimization problem, as can be formulated mathematically as in equation number 1. You can see that this, we are finding a minimum of the equation, but the constraint is that the sum of those intrinsic modes has to give us the original signal, that is x of t. And the same can be seen here. In spectral domain, the modes of the solutions are listed in equation number 2, and we can observe from there that the lower values of alpha, which is one of the parameters in VMD, will give us the higher frequency components, whereas higher alpha values will yield lower frequency components in the signal. What we have done is modes of VMD are used for extracting the brain waves with lower value of alpha, and with higher value of alpha, we have removed the low frequency artifacts. Based on the frequency ranges, gamma waves or alpha waves, beta waves are filtered, and these 5 waves are used for recognizing these 3 emotions. A 2-stage VMD with our optimal parameters can effectively remove LF artifacts and high frequency noises, and also enable 5 brainwave extraction. Now we can see here on the left is the first stage of the VMD, and the second is on the right you can see the second stage of the VMD. In the first stage, it can be seen that the VMD is applied on the EEG signal with k equal to 3, which is 3 intrinsic modes were extracted, and the value of alpha for that was 50,000, to demonstrate that higher values of alpha will get the low frequency components of the signal. And on the right, we can see that from that clean signal in stage 1, we have decomposed it into 5 frequency bands. So for a fixed EEG signal, it has been shown that it shows a Gaussian distribution in certain frequency bands, and the probability distribution function could be written as in equation number 4, and h of x is the differential entropy. And we have segmented the EEG signal into 1 second segments, and the feature is extracted from that signal. Now coming on to the CNN model. CNNs are extensively used for detection, classification, prediction of normal and abnormal events. 3 layers of architecture is being used: convolutional layer, pooling layer, fully connected layers. Now what I meant by that, CNN, that is convolutional neural networks, is a deep neural network which is generally used to classify images or 2D signals. In our case, we have an input that is a 2D signal. Now, CNN is extensively used for detection, classification, and prediction of normal and abnormal events. CNN generally consists of a 3-layer architecture, including a convolutional layer which filters the input, a pooling layer which reduces the dimensions of the feature, and a fully connected layer. The convolution layer uses a set of filters to generate a feature map which is processed by activation functions, which brings in the nonlinearity, and then a pooling layer which performs a feature reduction, or a dimensionality reduction if you will, and then a dropout layer which removes the percentage of connection between 2 consecutive layers in order to avoid overfitting problem. And then there is batch normalization, and a fully connected layer which flattens the high level features and combine all the features. And finally, there's a softmax function which generates the probability distribution for predicting the output class. And on the right, we can see the parameters, the hyperparameters for the trained CNN models. Now, this is a summary of the CNN models that we have used. Now, we have used 3 CNN architecture with different number of convolution layers, which is 2, 5, and 7. So it's a 2-layer, 5-layer, and 7-layer CNN model, in which I have used 4 activation functions, a ReLU, a leaky ReLU, an exponential linear unit, and a hyperbolic tangent. Stack of convolution layers are followed by fully connected layers and a classification layer. Stack of multiple convolutional layers can learn hierarchies of features. Now, in the figure, we can see that the D input, which is of the size 62 cross 250 cross 5, where 5 signifies the 5 frequency bands, or the characteristic frequency bands, and they're being fed to this 2D convolution layer, which is connected to a max pooling layer, and which is again connected to another layer of convolutional layer. Now coming on to the description of the dataset that we've used. The dataset is called the seed dataset, wherein we have 3 emotion classes, that is negative, neutral, and positive. And we have a total of 500 segments that we have used for training and 125 segments that we use for the validation. Now coming on to the performance of the CNN models. For a 2-layer CNN, we see best results with ReLU. And as we go on to different activation functions, we see that in ELU it's going to 78, And in a 5-layer, it's consistent across the board for different activation functions, but the highest is for ReLU, and again, that's 82. And for a 7-layer CNN, we have the best results, and it is consistent across different activation functions. And for ReLU, the best validation accuracy was found to be 90.30%. Now coming on to the class-wise validation accuracies. For a 2-layer CNN model, we had accuracies of 100% for positive emotion and 94% for negative emotion and 78% for neutral emotions. For 7-layer CNN, we have seen 88% accuracy for positive emotion, 94% accuracy for negative emotions, and 90% accuracy for neutral emotions. And for a 5-layer CNN, we have seen higher recognition accuracies of 91.30 for neutral, which is highest in all the models. But for positive and negative emotions, it has validation accuracy slightly on the lower edge. Now coming on to the performance comparison of our model with the existing literature that has been listed in table number 5, we can see that the first paper uses group sparse and canonical correlation analysis and have gotten an accuracy of 83.3%. And then we see another research group that has used discriminative graph and regularized extraction and they have got a validation accuracy of 79.88. And there's another group which uses a hybrid PCA and T statistics and have gotten a validation accuracy of 84.30. And then there's a group that uses differential entropy with dBn, SVM, LR, and KNN, and they've got best validation accuracy with dBn at 86.08%. And at last, the proposed method with DE features and CNN models, and we have gotten an accuracy of 90.33%, which is the highest among the existing methods. This method used differential feature extracted from 5 brain waves, which were constructed using VMD after removal of the low frequency artifacts. A 2-stage VMD with optimal parameters for the suppression of LF artifacts and high frequency noises and brainwave separation was proposed. We have created 12 CNN models with combinations of number of convolution layers and 4 activation functions. And we've also performed and evaluated all of this using seed dataset, computational complexity of the model, and validate using a wide variety of EEG databases. For the future scope, we can perform time complexity analysis of the algorithm and the models that we have used, and we could also validate this using a wide variety of EEG signals. Here, thanks to Ms. Shiva Ranjani for her kind support and guidance during the work carried out at IIT Palakkad. And these are the references. Thank you.